Okay, if you look at this problem, one of the things that certainly would have to be a concern is that the estimates were way off from what the truth was. And there was a statistician, mathematician named Gossett who looked at this, and there are some theories that have been developed to work with the variance, and he was bothered by it. And he came up with a rather sophisticated mathematical argument that we're going to have to basically say, believe us. And that argument said it will make more sense to calculate the sample variance if we divide by n minus 1 rather than n. And if we look at what happens here, rather than dividing 8 by 3, we would divide 8 by 2. And so the sample variance gets a little better. It comes up to 4. And here we would divide this, and it would be, say, 12.4. So we get a little larger variance. So now if we come back and we look at our estimates, rather than having 2 2/3 as the estimate, we have 4. Rather than having 8.2, we have 12.4. Now again, this isn't much better, and we did pick a problem to try and show some extremes. But in general, it will be better if you use this formula, and in fact it is the formula that is always used, to calculate out the sample variance. And we will leave it to whatever book you're looking at to go back and see an argument for this. So if we look at this problem, though, and we come back, and let's say you're going into your boss and we're looking at what's the cost of service. And you say to your boss, the average cost is $10. And the boss says, well, how much variability is there from the average? And you say, well, the average variability is 163. The boss, if she doesn't or he doesn't know statistics, might look at this and say, that's an awfully hard number. Average variation of 163. Maybe the boss says, well, what's the individual variability from the mean? We come back here and we say, well, the individual variability was 9, 9, 7, 5, 2, 2, and 30. And the boss may say, well, I'm a little confused here. The average variation was 163, but the individual variability never got over 30. Where's the problem? Well, the problem was these lousy minus signs. They were canceling out the pluses, and to get rid of them, we squared each number. So the 9 units of variation from the mean now became 81 units. The 30 units became 900. The squaring distorted the level of variation. And so the statistician said we have to undo this. So they came up with what was called the true standard deviation of the random variable x, the true standard deviation. And they gave this a symbol, and that is sigma of x. Now notice sigma of x doesn't have the square on it. And so what they did is they took the standard deviation is the square root of the variance. And we have the square root of the average variation, or the variance. So if you remember, we had gotten 163. If we approximate here, this would be 12.8. This would be the true standard deviation, a measure of the variability from the mean. If some of you have been involved with total quality movements, there is a 6 sigma that Motorola, Texas Instruments, and others use in terms of their quality. The sigma reverts back to the standard deviation. This, along with the mean, are the two most used numerical values that you will obtain. So if we look at this, the sample standard deviation then is just the square root of the sample variance. Now notice again, we're going to use the dividing by n minus 1 because it will tend to give us a better estimate of the truth. And so if we go through these problems, if you remember the variance for this set of data, the sample variance had been 4, the standard deviation would just be the square root of 4, which would be 2. And similarly, we had calculated out the variance for this set of data. And so the sample standard deviation is just the square root of 12.4. And here you have to trust me that I've used a calculator, and it's approximately 3.5. And so we now have, again, estimates. We had 2 sample standard deviations. We had 2 and 3.5, and the true standard deviation was 12.8. Now, again, the reason that there is this tremendous difference is the fact that our initial data had that one very large number. We had this 40. And when you study the theories of statistics, this is one of the things that you will study, is the idea of how large a sample do we need to take to adequately describe what is true of the population. Obviously, with a small sample such as 3, when there is a large amount of variability in the population, this small sample size is not going to be adequate. So again, summarizing, what we would like you to think about is statistics, results that are based on a sample, are used to estimate the truth. The truth is always based on a census. In statistics, the truth is always denoted by a Greek letter, and the truth is always a constant. Now, we're not considering how things will change over time, but there is only one true average and one true standard deviation. That is based on all the data having taken a census. The statistics are always random variables. So these are estimates of the truth. We would never bet our life on a statistic because we know if we take another sample, we would get a different value. And so our estimates would be different, but we hope that they're going to be close. When you study the statistics and look at the theories behind the statistics, you will learn about how large a sample is needed so that we get an adequate estimate. And this is what leads you into confidence intervals and other things that you may or may not have heard of. We'll stop there.